So, let us start lecture 61 part B, and the course is on phase diagrams in single component and binary systems. In part B, what we will be trying to understand the importance of free energy composition diagram. That will be the topic. If you go to part A, lecture 61, we have talked about peritectic phase diagram, and also we have talked about whether a phase diagram is drawn correctly or not, how to decide that. That one was also discussed. So, in the part B, we will be taking consideration of the Gibbs free energy of a solution as a function of composition, and try to see whether we can explain some of the important aspects of phase transformation. We will consider mainly two things. Looking at a complex phase diagram, whether we can actually draw corresponding free energy composition diagram, and we will take a consideration of a phase diagram, binary phase diagram with a congruent melting, and then we will try to see one important aspects of phase transformation, or you can say a phenomena that is called diffusion. And in diffusion we have two things, one is called uphill diffusion, another one is called downhill diffusion. So, with the help of Gibbs free energy composition diagram, we can actually explain that those two phenomena, okay, diffusion phenomena. So, we will try these two parts in this lecture. So, now if you see what we have done, we have taken a regular solution, model and binary system. We have considered A and B, these are the two elements, and we have taken actually the metals. X A and X B are the mole fraction. When you add them together, we are getting 1 mole of solution. And we are taking temperature and pressure constant, and every constant temperature pressure we are trying to draw the free energy composition diagram. So, pressure is kept always 1 atmosphere. So, that is the framework, and the equation what we are considering is G 2 equal to G 1 plus delta G mix, and we are trying to draw G 2 versus X B. Okay. And this gives me different shapes of plots, and then from there we are trying to assess equilibrium condition at each temperature, and that information we are reflecting on temperature X B plot. So, which gives me phase diagram. Fine, that is the main thing about the phase diagram, drawing phase diagram from Gibbs free energy composition plot. That is what we have done till now. Now, what we will try to see is, now we are given a phase diagram, and let us see whether you can go to free energy composition diagram. Okay. So, it is the other way around. Now, let us try to look at one phase diagram, it is a kind of schematic phase diagram. So, first thing, a given phase diagram, and then getting G 2 versus X B at different temperature, keeping when pressure is equal to 1 atmosphere. So, that is the thing we will be trying to do. Let us see a schematic phase diagram. Okay. This is X B, this is T, x a equal to 1, x b equal to 1. Now, I can have a phase diagram like this. So, we have a congruent point. Let us say this is my congruent point, and these are the two melting points. This is one, another one is this. Now, I can have two eutectic one eutectic is here, another eutectic, let us say and let us say this is TMB. Now, another eutectic, let us say it is happening here. Okay. So, now here we have, let us say, a particular phase which is gamma. This is liquid, this is liquid. Let us say this is alpha, this is alpha plus gamma, this is gamma plus beta, this is beta region, this is gamma plus liquid, this is liquid plus beta, alpha plus liquid, liquid plus gamma. Okay. If I take a phase diagram like this, and can we have, and this is literally, this is temperature corresponds to T congruent. So, this is congruent melting phase which is gamma, and it has melting point more than TMA as well as TMB. Now, let us say I choose a temperature, whether I can draw the phase diagram. So, if I choose a temperature, let us say I am choosing a temperature here. Okay. And another choice, this, let us see, this is the temperature we have chosen. Let us say this temperature is T1, and let us draw that free energy composition diagram. Now, since gamma is a congruent phase and it has the highest melting point in the phase diagram, that means as per our understanding, the gamma would have a very, very high negative del H mix value. So, if I try to draw corresponding phase free energy composition diagram at T1, I can draw like this. Let us say gamma, let me draw it a steep downward plot. Let us say this is gamma, G2 of gamma. Now, for alpha, so on the left side will be alpha phase. Let us say alpha is drawn with green color, or let us say the liquid is drawn with a green color. So, the liquid would be, let us say this is G2 liquid. Now, alpha phase, if I try to draw alpha phase, let me draw it with purple color. So, we have liquid phase, let me draw it little steeper. Let us say this is the alpha, G2 alpha, and this will be G2 liquid, and beta phase, if I try to draw with different color. So, let me draw it with this color. Let us say this is G2 beta. Let me draw this black one, the gamma. So, one common tangent will come here. I am just trying to draw schematically with this one is one common tangent. Another common tangent can be drawn with a red color like this, and here also one common tangent can be drawn like this. Okay. So now I see the composition. This is one composition, this is one, this is one, okay. These are the compositions which are falling on common tangents, and there are 4 common tangents. So, there should be 4 into 2, that means there should be 8 phases to altogether at temperature T equal to T1 corresponding to that phase diagram. Okay. So, this is x b equal to 1, x a equal to 1, this is G. Please understand that this is schematically drawn. We will just reflect those equilibrium composition over the phase diagram at temperature T1. So, now let us mark those compositions. This composition is Xb alpha in equilibrium with liquid. This is Xb liquid in equilibrium with alpha. Then in between we have liquid phase. Then we have Xb of liquid in equilibrium with gamma. Then we have Xb gamma in equilibrium with liquid. In between we have gamma phase. Then Xb gamma in equilibrium with liquid on the B rich side, and here also of liquid in equilibrium with gamma. This is Xb gamma liquid in equilibrium with beta, and this composition is Xb beta in equilibrium with liquid. Okay. So, we have reflected those compositions which are in equilibrium, and the first superscript is that phase what we are considering, and the second superscript is basically the phase with which the system is in equilibrium. Okay. And in between we have these two, we have gamma plus liquid. Here we have liquid plus gamma on the B rich side. In this zone we have liquid. Here we have liquid plus beta, and right side of it we have beta, and you use your judgment with the help of equilibrium plus the free energy hierarchy. And here if I try to see, this zone is alpha plus liquid, left to this alpha. In between we have already checked it's liquid, and between Xb liquid gamma and Xb liquid gamma liquid on the A rich side is gamma plus liquid. Let us see whether those compositions can be reflected on the phase diagram. So, one particular point is this point, which is Xb alpha in equilibrium with liquid. This one is Xb in equilibrium with liquid. Then we see the pink color. This one is Xb liquid in equilibrium with gamma. Then we have one more composition, which is this one. This is Xb of gamma in equilibrium with liquid. exactly the similar situation is appearing on the free energy composition plot. Then we have this composition which is XB gamma in equilibrium with liquid on the liquid rich side, on the B rich side. Then comes this point which is XB liquid in equilibrium with gamma. Then two more points, one point is this, another point is this. So, this is XB of liquid in equilibrium with beta, and this is XB beta in equilibrium with liquid. I could see all 8 points are reflected as per the equilibrium consideration in the free energy composition diagram. So, now you can see that even a phase diagram is given with your consideration, with your ideation, with a knowledge on free energy composition diagram, you can actually plot those equilibrium situations considering all the free energy plots. Now, here you see since congruent melting appears due to a very high stability of solid phase, you see here in this particular free energy composition diagram, the G2 of gamma has the most stability, because it is very steep downward, convex downward. Okay. And whereas those two terminal solid solutions alpha and beta, they have a very small range of solubility, that is what they are actually falling on the two extreme ends, and liquid everything would be miscible, that is what the liquid has a wide range. We can actually plot the G2 plot of liquid over the entire range. Okay. So, those considerations you can do. Like that way you can actually get to all the conditions. For example, I will just show one more plot at eutectic temperature on the A rich side. If I do that, then I think you can do for other cases also. So, let us see one more case. If I do it at this particular temperature, what will be, let us say T2. T2 is equal to T eutectic of alpha, okay, alpha rich side, let us put it that way. Okay. So, now if I try to plot free energy composition diagram, this is G, this is XB, XB is varying this way, XB equal to 1, XA equal to 1, this is T equal to T2, which is exactly matching with the eutectic line on the alpha A rich side, or alpha with alpha that eutectic that is forming. First thing I will draw the liquid line. I have drawn the liquid line. This is G2 of liquid. Now, I can draw gamma phase. This is gamma phase. Now, on the left side, the alpha phase and the liquid and the gamma phase will be merging each other. Okay. So, it will be falling on the common tangent. So, if this is, let us say this is G2 alpha. So, this is G2 of gamma, this black one is G2 of gamma, and the purple one is the G2 of alpha, and the green one is G2 of liquid. So, now I can draw a common tangent. Okay. So, these are the points where I am getting that common tangent. So, this composition would be XB alpha in equilibrium, XB alpha in equilibrium with liquid and gamma. This is XB liquid in equilibrium with gamma alpha. This is Xp liquid in equilibrium with Xp gamma in equilibrium with liquid alpha. So, right side of it, and on the other side I will have a situation which is drawn in this color. So, I will have a situation like this. So, the liquid line would be shifted above the common tangent between beta and gamma. So, if I draw a common tangent here, okay. So, this is not touching the liquid line. So, now we have two composition, one is here, another one is here. So, we have 5 compositions which can be shown, and so in between these two we have gamma phase. Okay. In between these two we have gamma plus beta, right side of it we have beta. Here we have liquid. In fact, over the entire range, this range, we have 3 phases which will be in equilibrium, liquid, alpha and gamma. All 3 phases will be equilibrium, and left to that we have alpha. Okay. So, let us see all those compositions can be reflected on the free energy on the temperature composition diagram. So, this is Xp gamma in equilibrium with beta, and this composition is Xp beta in equilibrium with gamma. So, what are those points? One point is this one, the another point is this one, this is another point, here is one point and here is one point. Okay. These compositions are Xb gamma in equilibrium with beta, this is Xb beta in equilibrium with gamma, this is Xb gamma in equilibrium with liquid and alpha, and this one is Xb liquid in equilibrium with gamma alpha, and this composition is Xb alpha in equilibrium with liquid gamma. Okay. So, now I could see there is good correspondence, unique correspondence with the free energy composition diagram drawn at T2 and the phase diagram at T2. So, like that way you can actually draw the free energy composition diagram even if a phase diagram is given. So, this is a congruent phase diagram example, and congruent melting is an unique example. Why? Because you could see here that the congruent melting phase, which is gamma, has melting point more than the melting points of those pure metals constituting that phase diagram. Such examples if you try to see examples, you can look at internet. One example is aluminum calcium phase diagram, where we have a congruent phase which is Al2Ca. And if I try to see the melting point, this is 660 degrees Celsius, this is melting point, and here the melting point is around 842 degrees Celsius, and this congruent phase melting point is around, this is 70 degrees Celsius. Another example is aluminum nickel system phase diagram, where we have a congruent phase called aluminum nickel. So, here also this is same as this. Nickel is, if I try to see melting point again, nickel is around 1455 degrees Celsius, and this phase has a melting point around 1640 degrees Celsius. Okay, so, around that. Now, here what is the advantage of this? Since this phase has a higher melting point, if that phase forms in the system of let us say aluminum nickel alloy, this phase will give you the high temperature strength, because this phase does not melt and it can hold its strength for a longer at a higher temperature. So, this can be useful in the application of making high temperature material. Okay. So, it can have a very high creep resistance, which is a very important deformation mechanism in case of materials. So, these are some examples, but what we wanted to learn is the correspondence with free energy composition diagram and phase diagram. Okay. So, now one more important aspect what we want to understand is diffusion phenomena. Diffusion phenomenon, okay. Or rather I would put it first downhill, which is very commonly observed, and uphill diffusion. This can be explained with the help of G2 versus X plot. Now, let us say I have a plot, simple plot, let us say this is x b, this is pure b, x b equal to 1, this is x b equal to 0. Let us say these are the two temperatures, these are the, and here I am drawing free energy composition diagram. So, the free energy composition diagram is developed in such a fashion that this is continuously, this is G2 of the solution, let us say solution. So, that is convex downward. So, this is let us say case 1, this is throughout convex downward. So, let us say I take two alloy compositions, one composition let us take this, let us say one composition I have taken this, another composition let us say I have taken this. These are the two alloy composition, this is x 1, this is x 2, these are the two composition with respect to solute B. Now, if I make the two alloy and let us say this is solid solution, this is solid solution free energy. Now, if I make these two alloys and then then I try to make a kind of a couple, diffusion couple we say, and then we heat it at a temperature which is where this free energy plot is experienced. Now, what would be the movement of elements? Okay. So, that let us understand. Now, for that first thing what we need to do is common tangent at those alloy compositions. One common tangent would be let us say passing through this, it extended, and let me extend this part, and another common tangent is going through this. Let us say I extend this, okay. So, this is extended and I extend this too also, this one also, okay. Fine. Now, I can mark those points, those cutting points with the common tangent at when the pure metal is experienced. So, here we can consider it as chemical potential. So, here G bar B of composition, let us say I just mark it as a composition x 2 should be, this is the value, and then here would be the value G B bar composition x 1. Similarly, here G bar A composition x 1 and this is G A bar composition x 2. Okay. So, these are the chemical potentials of A and B in the solution with composition x1 and x2. Now, we have made a couple. So, this is the couple we have made. One couple is this, another couple is this. Both are AB alloy, but here composition is x1, here composition is x2. So, let us say I plot chemical potential on x axis. This is G bar I am trying to plot. On the left side I am plotting A, and on the right side I am plotting G B bar. Okay. And this is the reference line, let us say. Okay. And this is the composition, let us say one composition here is x1, this is x2. Now, at x1 what are the chemical potential? This is Ga bar x1 and corresponding x2 would be Ga bar. I can mark it as Ga bar x2, and then here. So, this point should be drawn here, because as per left this free energy composition diagram, this would be Ga bar x1. Now, this would be Gb bar x2, and the corresponding, let us say this is my Gb bar x1, this point. Okay. These are the points, and this I can draw it like this. So, this is actually this particular thing with the composition x1. Now, if I try to see the variation of what is chemical potential, which is molar partial gives free energy of A in a solution, x1 is greater than Ga x2. I see that, and chemical potential talks about escaping tendency. These are actually nothing but escaping tendency of element. Fine. Here I could see from x1 chemical potential of A in x1 is higher than the chemical potential of A in x2. So, that means there is a gradient. So, there is a negative gradient of chemical potential. So, that would allow A to escape from x1 and go to x2 at a particular temperature T, this is at a temperature T. So, these two temperatures are same. Now, if xa this, that means that movement, the migration of A will take place from x1 to x2. Now, you see the x1, now let us see what is the x1 composition. x1 is rich in A, x2 is depleted in A, because composition A is varying this way. Now, as per the diffusion concept, we say that the diffusion happens from higher concentration to lower concentration. Okay. Here exactly that is happening. So, higher concentration of A, the phase with higher concentration, from there A is moving towards phase of composition, lower composition. So, this is actually typical, since higher concentration to lower concentration, it is the A migration is taking place, migration, or we can say diffusion or movement. This is nothing but diffusion. Fine. So, that is what this diffusion is called, downhill diffusion. So, that actually is decided by the chemical potential, higher chemical potential to lower chemical potential it is moving. So, let us see whether this downhill diffusion is applicable with respect to B, solute B. With respect to solute B, if I try to see Gb x2 is actually greater than GB x1, GB bar x1. So, that means B will move from or migrate from x2 to x1. So, x1 is rich in B and x1 is depleted in B. Fine. So, here also I see that the downhill. So, with respect to A, downhill is happening, and with respect to B also downhill is happening. So, downhill diffusion is nothing but migration of solute from higher concentration to lower concentration. Fine. So, we can explain downhill diffusion with the help of chemical potential. So, this case 1 is nothing but downhill diffusion. This happens when the free energy composition plot is continuously convex downward. Now, let us see whether we can explain with the upfield diffusion. So, the upfield diffusion, this is 2, this is upfield diffusion. As the name suggests, so that means the solute should move from lower concentration to higher concentration. Fine. Now, here I missed one point, let me just explain that point here. In case of downhill, as we see that the concentration will gradually, A part will move this way, so like this way and this way and this way. So, finally, they will achieve a common concentration. So, that could be placed here, which is x 0. So, that common composition once it is reached, then there will be no more diffusion, and in fact, this common composition is actually, if I draw this, they are actually these two tangents will merge each other. Okay. So, that means there is no chemical potential gradient. So, the diffusion, so there will be no net flow of solute from one phase to another. Okay. So, this is, so that means they will achieve one midpoint concentration where the chemical potential gradient will cease. So, that is the driving force there. Now, in this case, when I try to do it upfield diffusion, let us see, and the upfield diffusion happens if del H mix, let us say with reference to solid, is greater than 0. Okay. So, when greater than 0, let us see when, if it is at a moderately low temperature, we can have a free energy composition plot like this. This is G x b, x b equal to 1, x a equal to 1, this way x a is changing. Fine. The plot, if I try to see the plot, let us say the plot is like this. If the plot is like this, as happens in case of del H mix solid. So, here it is G 2 solid. Now, let us have a composition. Now, let me draw the common tangent. First, let me draw the common tangent. So, this is the common tangent and these are the two equilibrium phases. So, one phase is, let us say this phase is x b S 1 and S 2, let us say x b S 1 with reference to S 2, and this one is x b S 2 in equilibrium with S 1. These are the two compositions. Okay. This one composition and this is another composition. Now, I am taking two alloy system again. One alloy system, let us say here, let me draw it little shallow. Okay. So, one alloy system, let us say I am doing it here, this is one alloy, another alloy is here, let us say. Now, let us see if these two alloy, those blocks are made and diffusion couple is made, what will be the migration? This is at temperature T, let us say. Okay. First, what we have to do, we have to first try to plot the common tangent, not common tangent, here the tangent, because common tangent we have already seen, those are the equilibrium phases. If I do a tangent, so one tangent, let me just remove this arrowhead, so that otherwise this will be conflicting with that tangent. So, let us say this is one tangent. Okay. Another tangent is here. Okay. Now, let us mark those partial quantities. This is G B and these are the composition. This is x 2, this is x 2, this is x 1. So, this is G bar x 1 and this is G bar B x 2 and here G A bar x 2 and this one would be G A bar x 1. Similar way what we have done, let us plot that. These are the two blocks. These are the two blocks and this is G A bar, this is G B bar x 1 x 2. So, this is let us say G x 2 which is actually is there with the composition x 1 x 2 and this is, and another one is here let us say this is G A bar x 1. Now, for the G B bar, let us say this is G bar, let us say this is G B bar x 1 because x 1 would be here G B bar x 1 with the corresponding x 1 concentration. So, but we are reflecting on the x B side. Now, here it is G, let us say this point is G B bar x 2. Okay. G B bar, no, this one should be 2 and this one should be, this one is 2 and this one should be x 1. Okay. G B bar x 1. So, now okay. So, now let us see the relation. The relation would be with reference to A, let us consider, with reference to solute A. I could see that G A bar x 2 is greater than G A bar x 1. So, that means the escaping tendency of A from the alloy x 2 is more than the escaping tendency of A in x 1. So, A will migrate, this is at a temperature T, this temperature and this they are same. So, this migrate from x 2 to x 1. So, x 2 is depleted in A and x 1 is rich in A. Okay. So, now here you see that A is moving from lower concentration to higher concentration. So, lower concentration to higher concentration. So, this particular thing we call it, upfield diffusion. And where it will stop? If you see that they will start moving this way and this way, and this one also will try to move that way, because as we increase the concentration of A in x 1, okay. So, that means what I am doing, A is moving from x 2 to x 1. So, that means the composition is gradually moving this way, the A concentration. So, that means if I am here, if I am here like that way. So, let me put those points, these points, as we see that this particular line will gradually shift downwards. Similarly, with reference to B, let us see what is happening. So, with reference to B, with reference to solute B, I could see that G B bar x 1 is greater than G B bar x 2. So, B will migrate from x 1 to x 2 and from x 1 to x 2. And if I try to see composition, this is depleted in B and this is rich in B, rich B. So, that means the diffusion is taking place from lower concentration to higher concentration. Fine. So, this is also upfield diffusion. This is also upfield diffusion. Fine. But where it will end? Now, you see, as we have this situation, this kind of situation with the B, that means B is moving from lower concentration to higher concentration. So, the concentration will go towards right, As you go towards right, those points will move like this. Okay. These are the movements. Fine. So, I can do it with this. So, this previous case, the A was moving this way, this is A and here it will be B. So, as we are going towards the richer in B, this line, this particular line will move downwards. Okay. If you do all the tangents plot at different points as we increase the concentration of B. And finally, these two lines will actually merge with this line, this common tangent, and then we get those equilibrium compositions x b s 2 s 1 and x b s 1 s 2. So, there it will no more difference in the differences between these two will cease, these two will cease. So, system will reach equilibrium. Okay. So, here actually if we see the concentration on the A side, if I try to see x 1 with reference to A, it will get richer, and if I try to consider x 2 as with reference to B, okay, it will get richer. Fine. They will reach to finally, it will reach to x B S 1 S 2 and this one will reach to x B S 2 S 1 and these two will have equilibrium at temperature T. So, the equilibrium phase will happen. So, now this upfield diffusion, which is actually lower concentration to higher concentration movement of the solute, that happens when that inflection arises in the free energy composition plot. This is another important aspect for to understand some physical phenomena with respect to free energy composition diagram. So, now in case of downhill as well as upfield diffusion, if you see, though the movement of solutes are different in both the cases, but it is not violating any thermodynamic principle. So, thermodynamic principle for the migration of solute is always higher chemical potential to lower chemical potential. In both cases we could see the solute is moving from higher to lower chemical potential. There we are not violating any thermodynamic principle. So, let me close our discussion. We will continue our discussion and then finally, we will try to see the phase rule and that will be the end of our session. our course. Thank you.